Okay, so welcome to the second part of the marathon on permutations and combinations. We have another set of 10 questions that we will try to quickly cover. The questions again are from various different past papers, and you can follow the years at the bottom. Question one says find how many different numbers can be made by arranging all 9 digits of the number 2, 2, 3, 6, 6, 7, 7, and 888 if there are no restrictions. So whenever you have a question that has repetitions, always count the repetitions first. So that's 9 factorial. There are 2 2's, 2 7's, and 3 8's, and that should hopefully give you the correct answer. So 2 factorial 9 factorial divided by 2 divided by 2 divided by 6. That's 15120. Part 2. The number made is an even number. If you see the marks at the end of it, that sort of indicates that there's something that you need to be aware of. And you can't simply go on and say that there would just be, counting the numbers at the end and then sort of, get the correct answer. Remember that whenever you have repetitions, you need to be careful about what numbers you choose or based on the restrictions that you have. So all 9 digits. So I'm going to say that 1, 2, 3, 4, 5, 6, 7, 8, and 9. Let me just place that here so that's easier to see. Now what I know is that there's a restriction on the last digit. Okay, so can I say that the last digit could either be 2 or it could be 6 or it could be 8? Now I need to know specifically what it is so that I can count the repetitions in the rest of the digits as well. Okay, so let's say if there's a 2 here, that means that the 2 isn't repeated on the other dashes. If there's a 6 here, that means the 2 is repeated on the other dashes, and I need to divide that in order to not double count. So what I go on and do is I create cases out of this. I'm going to say that there are 3 different cases about this. I'm going to say that one is that the number could end with a One is that the number could end with a 2, the other is that the number could end with a 6, and the other is that the number could end with a 8. When it ends with a 2, the last digit is fixed. You don't need to count that in the permutations. There are 8 other digits, and I know that in these 8 digits there are 2 7's and there are 3 8's, so I need to divide that. When I take a 6 at the end, I know that there are 2 2's being shuffled, 2 7's being shuffled, and 3 8's being shuffled. Then when I go on and do this, I know that there are 2 2's, there are 2 7's, and now there are 2 8's. So there are 3 different cases, which is why this question is 4 marks. It's not just a simple question where you place the number at the end. Okay, so let's quickly try to do this. This gives me 3360. This gives me 1680. And it gives me 5040. Let's see what they make together. I think yes, we get the total correct. 3360. And I get 10080. That's the correct answer. Okay, then part B is completely different. Let's look at that. I have a bit of space crisis here. So what I'm going to do is I'm going to move this up so that you can see that the new working clearly now. You can scroll up and see part B. Okay. Sandra wishes to buy some apps for her smartphone, but she only has enough money for 5 apps in total. There are 3 train apps, 6 social networking apps, and 14 game apps available. Sandra wishes to buy at least one type of each app. Find the number of different possible selections of the 5 apps that Sandra can choose. Now there are set of apps that I need to choose from, and there's a lot of choice, to be honest. And let's try to do this. There are 3 train apps, 6 social apps, and 14 game apps. So what I'm going to do is I'm going to create a lot of cases here because it's 5 marks. I'm going to say that I start off with 1. There's 1 train app, there's 1 social networking app, and I have space for a total of 5 apps. So I'm going to buy 3 from here. Then I'm going to say that I change this middle number, and I say that I buy 2 from here and then 2 from here. Then I go on and buy 3 from here and 1 from here. So I think I've taken all the possible combinations where I have 1 train app. Then I could make this as 2, keep this as 1, and this as 2. Again, this as 2, this as 2, and then this is 1 again. And since I need at least 1 of each, that's all I can do. Then I could do 3, I could do 1, and I could do another 1 from here. Okay, so those are, I think, the possible ways of getting all these apps. Let's see if we get the correct answer. I'll have to write down combinations for each of these. 3C1, 6C1, and 14C3. 3C1, 6C2, and 14C2. 3C1, 6C3, and 14C1. 3C2, 6C1, and 14C2. 3C2, 6C2, and 14C1. 3C3, 6C1, and 14C1. So that's a pretty long calculation. Let's try to do that. 14C3, 6552. $4095. $840. Three, 8. $630. 94. Let's see if adding all of this gives me the correct answer. Now, since this is a 5-mark question, calculations might take a little bit, but that's part of the question then. And I get my total 13839. Okay, so that's the first question that we have here. Let's move on quickly to the next question. This says a chess team of 2 girls and 2 boys is to be chosen from the 7 girls and 6 boys in the chess club. Find the number of different ways this can be done if 2 of the girls are twins and either both are in the team or both are not in the team. Okay, so let's try to figure that out. I think that's a fairly simple question. If I let's separate the twins, or the girls are twins. So what I'm going to do is I'm going to say that they can be either twins or girls or boys. Then there are 5 because 2 of the girls are twins. 5, 2, and 6 boys. Okay, and I need a team of 2 boys and 2 girls. So either both are in the team or both are not in the team. So 2 and 2 and another 2. Okay, so I can either have both the twins in the team, in which case I have both 2 and then 0 girls from the other group, and so the boys are sort of 2 in each case because that's what the team is made about. 2C2, 5C0, 6C2, 2C0, 5C2, and 6C2. So let's see, 6C2 gives me 15, and 5C2 into 15 gives me 150. So I get a total of 165. Okay, then part B says the digits of the number 1, 2, 4, 4, 6, 8, 7 can be rearranged to give many different 7-digit numbers. How many of these 7-digit numbers are even? Now again, I need to be careful. Why? Because there are 2 4s in the middle, which is something that I have to be very careful about, because repetitions cannot be counted twice when you are sort of filling out the restrictions. Okay, so let's do this. Let's copy thrice. I would also do 2 cases, but I find it more convenient to explain in 3 cases. I'm going to do that. I'm going to say that there's a 2 at the end, or a 4 at the end, or a 6 at the end. Oh, there's a 4th case as well. I didn't see the numbers carefully. And there's 8 at the end. Okay, so if the 2 is here, then that means that the 4 was repeated, so I get 6 factorial divided by 2 4s, which is 2 factorial. If the 4 is at the end, then nothing got repeated, so there's no division there. Then it's again 6 factorial, because the 4's got repeated, 2 factorial. Again 6 factorial divided by 2 factorial. I could have bunched these cases together, the 2, the 6 and the 8. That's up to you. If you can figure that out, go ahead and do that, and that should still give you the correct answer. I'm just adding all of them up. Gives me a total of 1800. Okay, let's look at part C. Oh, there's part 2 as well. It says part 2. It says how many different numbers between 20,000 and 30,000. So I'm talking about 5-digit numbers, 1, 2, 3, 4, 5. Between 20,000 and 30,000. That simply means that you can just have a 2 at the start. Why? Because no other number can be between 20,000 and 30,000 if the number has to be between 20,000 and 30,000, it must start with a 2. Okay, there's no other restriction, is there? It can be formed using 5 different digits from the digits 1, 2, 4, 6, 7, 8. Now, what you need to see is it says 5 different. So I can't really double count 4s in this case, and the 2 is already gone. Okay, so I'm left with 1, 4, 6, 7, 8. There are 5 digits. I have 4 places. I can fill them up like this: 5C1, 4C1, 3C1, and 2C1. Okay, and that should give me 120. I can also say 5C4 into 4 factorial. I'm choosing 4 out of the 5 and I'm arranging them. Okay. Then this part C. It says Helen has some black tiles and some white tiles and some gray tiles. She places a single row of 8 tiles above her wash basin. Each tile she places is equally likely to be black, white, or gray. Find the probability that there are no tiles of the same color next to each other. Okay, now remember that this is a probability question, so I need to work through it like a probability question. Now, the reason I cannot calculate permutations of these tiles is because I don't know the exact number of tiles that are available to me. It just says I have to arrange 8 of them. I don't know how many grays were there, how many whites were there, and so on. The only thing that I know is that I have a sufficient number, and what I need to do is I need to make sure that I don't place the same colored tile next to each other. So let's say I was placing 8 tiles. Let me just make 8 dashes. Okay. Now I can say that any of the tiles could come up at the start. So there's a 3 out of 3 chance that the first tile is either gray, white, or black. Now, whichever tile I place here on the first dash, I cannot place the same tile next to it. So the number of choices then is reduced by 2 out of 3. So let's say I placed a gray tile on the first one, I could not place it on the next one. So the next one is then just two different colors available to me. Now, whatever tile I place next to it, they that color can again not be repeated. So there are two other colors that I can then go on. So that keeps happening. I have just a choice of two colors on the next tile. So that becomes 1, 2, 3, 4, 5, 6, 7. So that's 2 over 3 power 7 into basically 1 into 2 over 3 power 7. What does that give us? Does that give us the correct answer? Let's check. It gives us 0.0585 or 128 over 2187. Okay, and that is the correct answer. Okay, then moving on to question number 3. It says 9 cards are numbered 1 to 2 again. I noticed that there's a repetition there and there are 3 sixes here. All 9 cards are placed in a line, making a 9-digit number. Find how many different 9-digit numbers can be made in this way if the even digits are all together. Now, I don't need to place them at the end. I just need to put them in a box, which is then an advantage right now because I don't need to think about a lot of cases there. So 1, 2, 3, 4, 5, 6. There are 2 2s, 1 4, and 3 6s. So 6 numbers go inside, 3 numbers come outside. The box becomes a dash. So this becomes what? This becomes 4 factorial divided by 2 factorial into 3 factorial. Okay, let's see if that gives us the correct answer. I have 4 factorial divided by 2 divided by 6. Oh, I forgot to shuffle the ones inside the box. Okay, and I also forgot 2 factorial, 2 2s, 2 3s, and 3 6s. It's just a silly mistake. That gives me 720. Part B. Part B says if the first and last digits are both odd. Okay, so I need to place an odd number right at the start and at the end as well. So that sort of tells me that there might be a few cases involved. So I'm going to just think about the cases once I put in the dashes. There are supposed to be 9 of these. 5, 1, 6, 7, 8, 9. Okay, so odd numbers that I have available are 1 and 3. So there could be a case where I have a 1 at the start and a 3 at the end, and there could be another case where I have a 3 at the start and 1 at the end. So I need to be able to do both of those cases. They're more or less the same because it's really the even digits that are more tricky in this question. The odd digits seem reasonably fine. So I have 7 dashes in the middle, so 7 factorial divided by 2 factorial into 2 factorial. No, sorry, the 3's aren't getting repeated, so I'll ignore those into 3 factorial. And then 7 factorial, the 2 2's are being repeated and the 3 6's are being repeated. So I get 7 factorial 2 into 6 into 2. I seem to have made a mistake somewhere. Oh, there's a third case involved. Oh, my bad. I could have a third case as well, where I have a 3 at the start and I have a 3 at the end as well. So that's another case. So in that case, that's 7 factorial over 2 factorial into 3 factorial. So 840 plus 420. That gives me 1260. Yeah, that's the correct answer then. Okay, there's a third case involved as well. So just make sure that you count that as well. Okay, moving on. When we have part 2, it says 3 of the 9 digits are chosen and placed in a line, making a 3-digit number. Find how many different numbers can be made in this way if there are no repeated digits. So that seems fairly simple. So I don't count the 2's twice, I don't count the 6's twice, I don't count the 3's twice. So I just have 1, 2, 3, 4 and 6 to choose from. So I can simply say that if there are no repeated digits and it's just a 3-digit number, so I have 5C 1 2 3 4 and 6. Sorry, that's 6. I have 5 digits to choose from, so that's 5C1, 4C1 and 3C1. That gives me 60. If the number is between 200 and 300, now notice that here I'm not talking about repeated digits, so I need to be careful about this. The number is between 200 and 300. That sort of fixes the idea that the first digit has to be a 2. There can be no other digits. What I need to be then careful about is that I am allowed repetitions. So I could have numbers that say, for example, 233, and I could have another number that says 266. Okay, and then I can say that this is one possibility, and the third possibility is that I could have two numbers and I could have completely two different digits appearing here. So I could say that this is basically 5C1 and 4C1. What I want to just emphasize here is that that you need to be aware of the fact that when you have repeated digits, you can't just simply count them inside the combinations. I couldn't have said 7C1 into 6C1. Why? Because I would be double counting the 3's, I would be double counting the 6's. So I just need to make sure that wherever the digits are being repeated, I count them out separately. So I get a total of 22. Okay, and that's the correct answer. Moving on to question number 4, it says the shop has 7 different mountain bicycles, 5 different racing bicycles, and 8 different ordinary bicycles on display. A cycling club selects 6 of these 20 bicycles to buy. Now remember that they're all different. How many different selections can be made if there must be no more than 3 mountain bicycles? And no more than each of the 2 other types of bicycles. So 7 mountain, racing, and ordinary. Okay, let's write the totals first. 7, 5, and 8. I need to buy 6 of these. Okay, so I mean, if there must be no more than 3 mountain bicycles and no more than 2 of each of the other types of bicycles. So that's a little complicated. So there are 4 marks for this. Let's start thinking about this. So the mountain bicycles can be 3, and I could have one of this and no more than 2. Okay, 3, 1 and 2. Then I could have 3, 2 and 1. Then I could have 3, 2. I could select no more than 2, so that's 2, 2 and 2. So I have 3 different cases here to choose from. It's 7C3, 5C1 and 8C2. 7c3, 5c2, and 8c1, and 7c2, 5c2, and 8c2. So there are three different cases. The question's wording seem a little odd now. It should say somewhere that I want to buy all three different types of bicycles. I will certainly check back on the marking scheme and see what it says regarding the examiner's review. This is 4900. $2,800 and $13580. Okay. It says part 2, the cycling club buys 3 mountain bicycles, 1 racing bicycle, and 2 ordinary bicycles and parks them. So they've bought a total of 6 bicycles, which has a row of 10 empty spaces. How many different arrangements are there in the cycle rack? If the mountain bicycles are all together and no spaces between them, the ordinary bicycles are both together with no spaces between them, and the spaces are all together. So what I'm going to say is that the 3 mountain are in the box, then the 2 ordinary are also in a box, the spaces are also in a box, so I have 4 empty spaces in a box, and the racing cycle is then outside. So I have a total of 10 spaces, but 3 of those have converted into a box. I'm going to say 3 factorial, I go into the box, another 3 factorial, I go into the second box, that's another 2 factorial, and then 4 factorial. Now remember that the and with the dashes I should have done that before, 4 factorial, and remember now that the spaces are identical but the rest of them are not. So I've done 4 factorial because there's 1 dash outside and there are 3 boxes. Then I go inside the box. I think I've written this wrong. I should have written 4 factorial instead of 3 factorial. That's the mistake that I made. So 4 dashes, so 4 factorial, then inside the box that's 3 factorial, then 2 factorial, and then 4 factorial for the spaces. Now I divide by 4 factorial because the spaces are identical, and you shouldn't be counting this permutations, but just as a rule of thumb I usually do, and then I divide it because that feels more logical to do in all sorts of questions. Let's see if I get the correct answer. Yeah, I'm getting 288. Then part 3 says how many different arrangements are there in the cycle rack if the ordinary bicycles are at each end of the bicycles and there are no spaces between any of the bicycles. Now what I need to understand is that there is a group of bicycles that are standing together. 1, 2, 3, 4, 5, 6. Now there are spaces outside that I need to be aware of. So what I'm going to do is I'm going to say that this becomes 5 factorial and divided by 4 factorial. Okay, what's happening inside the box is that both of these are ordinary. Now I don't know which ordinary is on the first one and which ordinary is on the last one, so I'm going to say that that's 2c1 into 1c1. I'm filling out the dashes. Okay, 2c1 into 1c1, 2c1 for the first dash, one of the ordinary bicycles comes up there and the other ordinary bicycle comes up at the other end. Then what I need to then do is the rest of the dashes are fixed. I know that the other 4 bicycles are there, so I'm just going to say 4 factorial. See if that works out for us. 5 factorial. The answer is 240 and I'm also getting 240. Okay, moving on to question number 5. It says 7 friends together with their respective partners all meet up for a meal. To commemorate the occasion, they arrange for a photograph to be taken of all 14 of them standing in line. How many different arrangements are there if each friend is standing next to his or her partner? Okay, So what I need to do is I need to make 7 different boxes. Now that's a task. So I'm going to use the copy and paste. Let me just draw one box at least. Okay. Just putting out 7 boxes, although unnecessary, but to show such detailed working, you can imagine the boxes and sort of do it as well. Each of the boxes has 2 dashes. So that's 7 factorial into 2 factorial into 2 factorial into 2 factorial. Because they can shuffle around between themselves, they just can't leave the box. It's 5, 6, and 7. So I get 7 factorial into basically 2 to the power 7. 6, 4, 5, 2, 1, 0, 1, 2, 0. Then part 2. How many different arrangements are there? The 7 friends all stand together and the 7 partners all stand together. That's relatively simple. So 2 dashes, 2 factorial, then inside the box. 7 factorial into 7 factorial. Quite a huge number. 50803200. Part B. A group of 9 people consists of 2 boys, 3 girls, and 4 adults. In how many ways can a team of 4 be chosen if both boys are in the team? So boys, girls, and adults. Okay, I need a team of 4. Both the boys are there, so 2 out of 2. Then since there's no discrimination between girls and adults, what I can say is that there are others. So I can simply say that there are 7 other people and 2 need to be chosen. So I'm going to say 2C2 into 7C2. Rather than making up a lot of other cases, I can just simply do this. It gives me 21. The adults are either all in the team or all not in the team. So now what I need to be aware of is that I'm quite aware of the adults. So 4 adults. They are either all in the team or all not in the team. The others is 5. The girls and boys together are 5. So adults are either in the team, all in the team, in which case I need no one else. If they're not all in the team, then I need 1. So this is 4C4 and this is 5C4. I can ignore the zeros if I want. That gives me 1 and 5C4 should give me 5, I think. Yeah. So I have a total of 6. Then it says part 3. At least 2 girls are in the team. So at least 2 girls. So I'm just now counting the girls and the others. So at least 2 girls. Out of 3 I need 2. The others are in this case 6. So 2 girls, then 2 others, then 3 girls and 1 other. There can be no other case. 3C2 into 6C2 and 3C3 into 6C1. Let's see if that gives us the correct answer. 3C2 into 6C2. That gives us 45 plus 6. And that's a total of 51. So that's another question then, more or less the same as what we've done in the past as well. Now, let's look at this question. This is one of the most trickiest questions that you can come up with in your past papers. This is from November 10, 6-3, question number 6. It's going to take a little time to absorb, so if you don't understand it, just rewind the video and see it again and see if you understand it then. Okay, I'll start off with part 1. It says a small airplane has 14 seats for passengers. The seats are arranged in 4 rows of 3 seats and a back row of 2 seats. 12 passengers board the plane. How many possible seating arrangements are there for the 12 passengers? Giving your answer correct to 3 significant figures. So there are 14 seats. I can simply say that they all walk in, choose their seats, and seat themselves. So 14 seat 12 into 12 factorial. So 3 significant figures. So I can say that this is 4.36 into 10 to the power 10. Yep. Then part 2 says there are 12 passengers consisting of 2 married couples, Mr. and Mrs. Lin, Mr. and Mrs. Brown, 5 students, and 3 business people. The 3 business people sit in the front row. So that's business 1, business 2, and business 3. They've all taken their seats. The 5 students each sit at a window seat. Mr. and Mrs. Lin sit in the same row on the same side of the aisle. Mr. and Mrs. Brown sit in another row on the same side of the aisle. How many possible seating arrangements are there? So one thing that's obvious is that the couples can either sit here, here, or here. So what they need to do is the couples need have lesser choices here. So what I'm going to say is let's first talk about the business people. They have their seats fixed, but they still need to arrange themselves. So 3 factorial. 3 business people are already seated. Then Mr. and Mrs. Lin sit in the same row on the same side of the aisle. When Mr. and Mrs. Lin come in, they have 3 rows to choose from. So they end up choosing one of the rows and they arrange themselves. Then come Mr. and Mrs. Brown. They again have now 2 rows to choose from because one of the rows is occupied by Mr. and Mrs. Lin and the other is occupied by the business people. So that's another 2c1 into 2 factorial. Then what needs to happen is the other 5 students sit down on the window seats, so that's 5 factorial. I missed out the 2c1 because I didn't get the couples to sit one by one. I should have done that. Whenever you have a question like that, just do that. 6 into 3 into 2 into 2 into 2 into 5 factorial. Yep, that gives me the correct answer, 17280. Okay, then this last part is very tricky. It says if instead the 12 passengers are seated randomly, find the probability that Mrs. Lin sits directly behind a student and Mrs. Brown sits in the front row. So that is very tricky, and just please make sure that you follow the working that I'm doing in order to understand this question. The first thing that it says is there's a probability. So what I'm going to divide it by is the answer from the first part, because that's the total unrestricted arrangements that are there. Let's see. If Mrs. Lin sits directly behind a student and Mrs. Brown sits in the first row, so I know that Mrs. Brown needs to come in and choose one of these 3 seats. So I'm going to say that 3c1. Now let's assume that Mrs. Brown takes up this seat. Now what Mrs. Lin does is she sits directly behind the student. So can I say that Mrs. Lin and the student are then sitting in a group like that? Okay, let me draw it with the blue colored. Okay, so they could either be sitting here or sitting here or sitting here. That's 4, 5, 6, 7, 8, 9, and 10 different positions. Okay, let me count that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there are 10 different positions that Mrs. Lin and the student could arrange themselves. 10c1. But any of the students could be sitting with her, so that's another 5c1. She needs to be sitting directly behind a student. I don't know which student, so I've selected the student as well. Now, one of the students is seated. Mrs. Lin is seated. How many other people are then left? And Mrs. Brown is also seated. So 3 people are seated out of 12. So 9 are left. how many seats am I left with? I had 14 seats. So I'm going to say that I am left with 11 seats. So the other 9 people come in, 11C9, and sort of arrange themselves. And the denominator is then answer from part 1. Okay, so I'm going to use that answer. I'm going to say that that was basically 14C 12 into 12 factorial. Let's see if I get the correct answer. So 3C1 into 10 into 5 into 11 C9 into 9 factorial divided by 14C 12 into 12 factorial. Yep, I get the correct answer. That's 0.0687. Okay, tough question. Please make sure that you review this before moving on. Then comes another tough question. It says question number 7. This is about pegs. Are to be placed in the holes in the 4 holes shown, 1 in each hole. The pegs come in different colors and pegs of the same color are identical. Calculate how many different arrangements of colored pegs in the 4 holes can be made using 6 pegs, all of different colors. So what I'm going to say is I just need to select 6C4. I need to just select the 4 colors, and then I can just multiply it with 4 factorial. So I'm just choosing the color and multiplying it with the arrangements. So 360. 4 pegs consisting of 2 blue pegs, 1 orange peg, and 1 yellow peg. Now I have the colors fixed in front of me, and I see that 2 of those are also identical. So I'm going to say that's 4 factorial over 2 factorial. So I think that's relatively simple. That's 12. Now it says barrel has 12 pegs consisting of 2 red, 2 blue, 2 green, 2 orange, 2 yellow, and 2 black pegs. Calculate how many different arrangements of colored pegs in the 4 holes barrel can make using 4 different colors. So let's see how many colors do I have. 1, 2, 3, 4, 5, and 6. So I can say that if I want all 4 different colors, that's the same answer as the one above. I think 64 into 4 factorial. Now, so in part 4, it says 3 different colors. So what I need to understand is that I'm choosing 3 different colors. So 63. Now, when I'm arranging them, what I need to be aware of is that I am arranging all 4, but each color would be repeated once. So each of these combinations will have one of the colors repeated. I don't know which color, but I know that there will be 3 different colors that will be repeated. So what I'm going to say is that if I was, let's say the green, let's say the red was repeated, I would divide by 2 factorial. But I don't know for sure whether the red was repeated. So each of the 3 colors that was chosen in 6C3 could be repeated. So I get multiplied by 3. Why? Because there are 3 different colors that could each be repeated, and if they were repeated, they need to be divided by 2 factorial. Slightly more difficult to understand, but try to imagine the cases like in part 2. If you imagine it's something like part 2. Apart from the fact that it couldn't just be blue, orange, and yellow, it could be red, blue, and green, or red, blue, and yellow. So there could be a lot of cases to list down, but I can't go on and list all of them because that would be very tedious. 63 is a huge number to sort of list down. So that is what you need to be aware of. Then part 4 says any of her 12 pegs. So any of her 12 pegs means 4 different colors. So I'm going to say that that was 720. 4 different colors, that's 360. 3 different colors, that's 720. Okay, then I have 2 different colors. I would also have 2 different colors. That is something that I need to calculate. So what I'm going to say is 62 into 4 factorial into 2 factorial into 2 factorial. So each of those colors was repeated twice. So I'm going to say 6C2 into 4 factorial divided by 4. Okay, and that should get me the correct answer. Why didn't I have to multiply by 2 in the last case? Like in the last case, I did not know which color was being repeated, because there were 3 different colors. In this case, that I know that since there are just 2 different colors, each will be repeated twice in every combination that I get, so I don't really need to multiply with the different situation here. So I get a total of 11, 70. And that's the final answer. Moving on quickly, question number 8. It says find how many different numbers between 3000 and 5000 can be formed from the digits 1, 2, 3, 4, and 5 if the digits are not repeated. Okay. So the first digit could either be a 3 or a 4, so that's 2C1. Okay, I had a total of 5 digits and one of them is gone, so I'm left with 4 digits: 4C1, 3C1, and 2C1. So that gives me 48. Then part 2 says if the digits can be repeated and the number formed is odd. Okay, so 1, 3, and 5 could appear here, but that doesn't change anything for the rest of the digits. I still have 5C1. Oh, okay. Oh, I forgot the other restriction. Okay, there is this other restriction that says they could be just starting with 3 and 4, so that's another 2C1. But the fact is that since the digits can be used twice, it doesn't matter. 2C1 and 3C1 fit on the last 2 dashes, and then for the other dashes, I have 5C1 choices and 5C1 choices. So that's 5 into 5 into 3 into 2. Yep, that gives me 150. Then part B, a box of 20 biscuits contains 4 different chocolate biscuits, 2 different oatmeal biscuits, and 14 different ginger biscuits. 6 biscuits are selected from the box at random. Find the number of different selections that include the 2 oatmeal biscuits. So I think that's a reasonably easy question. Chocolate, oatmeal, and ginger biscuits. Okay, they're all different. So 4 to 14. I don't really need 2 separate categories for this question. I can just combine them and say that there are others and oatmeal. Yeah. So there are 18 others. I need to select the 2 oatmeal definitely, and I need to select 4 more, so that's 18C4 into 2C2, and that should give us 3060. Okay, then it says part 2, find the probability that fewer than 3 chocolate biscuits are selected. So the denominator, remember, has to be unrestricted combinations. So I'm just going to write 20C6 at the end in the denominator. Fewer than 3 chocolate biscuits are selected. That means I need 2 chocolate and others. So I'm going to say that there are 4 chocolates and there are 16 others. So fewer than 3 chocolate biscuits. So that's 2 and 2. That's 1 and 3. And that's 0 and 4. I could have all of these combinations. I could say that 4C2 into 16C2, and then 4C1 into 16C3, and 4C0 into 16C4, and all of this divided by unrestricted combinations 20C6. Oh, why have I taken 6 biscuits? Oh, my bad. You just make that correction. 2 and 4, 1 and 5, 0 and 6. I thought that I was selecting 4 biscuits, but I'm selecting 6 biscuits. 20C6. I get 0.939. Okay. If you want to write it out in decimals, it was 910 over 969. This question number 8. We're quickly on to question number 9. It says in an orchestra there are 11 violinists, 5 cellists, 4 double bass players. A small group of 4 musicians is to be selected from these 20. How many different selections of 6 musicians can be made? If there must be at least 4 violinists, at least 1 cellist, and no more than 1 double bass player. Okay, I will need to make cases. Violinists, cellists, double bass players. 11, 5, 4. 6 musicians are to be selected. At least 4 violinists and 1 of each. So 4, 1 and 1. And there can't be another case. 4, 1 and 1 is the only case. And no more than 1 double bass player. So there could be more cases. Yeah, I thought at least. So I can have 4, 2 and 0. I can also have 5, 1 and 0. Okay, that gives me 11C4, 5C1 and 4C1. 11C4, 5C2 and 4C0. 11C5, 5C1 and 4C0. Okay, 11C4 into 5 into 4, that gives me 6600. 11C4, 5C2. One, two, two, 1, 0. Okay. Then it says a small group that is selected contains violinists, 1 cellist, and 1 double bass players. They sit in a line to perform a concert. How many different arrangements are there of these musicians if the violinists sit together? I think that's a reasonably simple question. The violinists need to be in a box. 1, 2, 3, 4. Okay, that's 3 factorial into 4 factorial. That's 24 into 6. I think that should give you 144. So reasonably easy at the end. Okay, the last question for this marathon then, that's where it ends. Mr. and Mrs. Keen and their 5 children all go to watch a football match together with their friends. Mr. and Mrs. Uzma and their 2 children find the number of ways in which all 11 people can line up at the entrances in each of the following cases. Mr. Keen stands at one end of the line and Mrs. Uzma stands at the other. So MK and MU. There are a total of 7 here and 4 people here, so there are 11 people in the line. So I have 9 dashes in the middle. Okay, no other restrictions. I think that's fairly simple then. It should just be then Mr. Keen stands at one end of the line and Mrs. Uzma stands at the other end. So it's just that I need to think about the fact that they could be standing this way as well. So I could have Mr. Keen stand at the end because the end is not fixed. It doesn't say the start or the end. So Mr. Keen. So I have just two different cases. I'm going to say 9 factorial for this one as well and 9 factorial for this one as well, and I can get a total of 725760. Then part 2, it says the 5 Keen children all stand together and the Uzuma children both stand together. Okay, now there's no restriction on the ends in this case, so it's just that I need to put the children together. 5, 1, 2, and then there are 4 other people outside, the adults in this case. Since there are a total of 11 people, I get 2 dashes and 2 boxes and 4 dashes, so that makes a total of 6 factorial, then inside the box, and then 2 factorial for another inside the box. So I get 6 factorial into 5 factorial into 2 factorial, 172800. Okay, that is the end of the marathon. Please make sure to like the video and subscribe to my channel for more content. Thank you.